Okay. Hello. Welcome to our degree seminar. Today our speaker is Aleksandra Olejak. She is our student, and she was do PhD in ZAMP with Chris Garching. Now she's postdoc in MPIA in Garching. Ola, floor is yours.
Thank you for this introduction, and thank you for having me here. I hope that you can hear me on Zoom as well. It's been years since I completed my master's thesis here in the Warsaw Observatory, and that was a nice time. It's nice to be back here. So today I will talk about the binary black hole mergers, those that comes from isolated binary evolution of massive stars and are expected to contribute to the population of gravitational wave sources detected by LIGO-Virgo-Kagura collaboration. So the evolution of massive stars is accompanied by interactions in binary systems. We expect that for example, mass transfer could leave some characteristic fingerprints in the distribution of later form binary black hole mergers parameters. So first, let me start with some brief introduction to current state of gravitational wave detection. So right now we have around 90 publicly announced detections of double compact object mergers, and due to their masses, they are vastly dominated by binary black hole mergers. However, there are also a few candidates for black hole neutron star mergers and 2 events classified as the binary neutron star mergers. So there has been there has been 3 completed observational runs, and right now, since May 2023, there is the run 04. So probably, you know this famous plot, and you have already seen it several times. However, it is a nice summary of the currently known masses of compact objects. So with the blue dots, we have masses of black holes derived from gravitational wave detections, while with the red dots, we have the black hole masses inferred from electromagnetic wave observations. And as you can see, there is some interesting difference in the mass distribution of those 2 different subpopulations. And those black holes that are inferred from gravitational wave detections tend to have higher masses in general than those that are inferred from electromagnetic wave observations. It could be partly due to the selection bias. However, also the progenitors of gravitational wave sources are expected to evolve in the lower metallicity environments, and this could also explain the difference in their masses. There are a few objects in the lower mass gap which are mainly obviously products of binary neutron star mergers. So what actually LIGO-Virgo-Kagura collaboration matters? So with the detection, they also provide some estimates on the individual masses and mass ratio of the system. However, the parameter that is most easy to derive from the data is called Chirp mass, and this is why this parameter is usually given with a much better precision than the individual masses of the merger. So this peak mass is some combination of the individual masses with the given powers. And there's a similar situation with the spins of gravitational wave sources. So LIGO provides some estimates, for example, for magnitudes of the individual components. However, the parameters that is measured with the best precision is usually effective spin, that is some sort of linear combination of the individual spin magnitudes weighted by the masses of the components and the cosine of the angle between individual spins and the orbital and momentum houses. So now with the increased number of detections, LIGO also tries to check, for example, if they would see some sort of evolution of parameters like the total energy rates with the redshift. So to, for example, check if this evolution of the rates follow the star formation rates in the universe, and it looks like so far it is consistent, which points towards the stellar origin of those sources. And they also provide some report on some possible correlations between different parameters, like, for example, masses and spins that could also indicate on some astrophysical process ongoing during the formation of gravitational wave sources. So, yeah, together with the detections, LIGO also tried to derive some sort of mass distribution for the population. So here is a distribution of mass of the more massive black hole from the binary black hole mergers. Once trying to get rid of the selection biases, so based on some Bayesian interference. And as you can see, there are those two characteristic peaks in this distribution. Those peaks were already reported by the previous catalog of gravitational wave sources, which could point towards astrophysical origin of those features. And there are several candidates for the processes that could be responsible for the formation of such peaks. For example, this first peak could be some indication of some specific mechanism during core collapse or due to binary interactions, and the second peak, around 35 solar masses, could have something to do with so-called crane stability supernova or binary interactions, or could also indicate contribution of some other formation channel that favors formation of more massive black holes. And then after the second peak, we have this long tail towards very high black hole masses. So right now, we don't really know what is the origin of those detected population of binary black hole mergers. There are several formation channels proposed by the recent literature, and I think the most popular ones are isolated binary evolution. So the classical isolated binary evolution channel with common envelope, and recently gaining popularity channel with so-called stable mass transfer channel. However, also promising formation scenario is dynamical capture in the dense stellar environments, such as globular clusters, or, for example, formation in the AGN disk. There are also some more exotic formation scenarios, like, for example, some contribution of the primordial black holes. So today, I will focus on this isolated binary evolution channel in two variants, with and without common envelope phase. And here is the plot, quite popular plot, that demonstrates that while low mass stars are likely to be found like a single stars and evolve like a single stars, the massive stars, such as neutron star or black hole progenitors, are much more likely to be found in the binary system or in the triple system. So this justifies why binary interactions are so important once studying evolution of the massive stars. So when you're part of the community or you had something to do with the gravitational waves, probably the first thing that comes to your mind when you think about isolated binary evolution channel for binary black hole formation, you would think about this evolution through the common envelope phase. So common envelope phase seemed to be a promising mechanism in order to bring initially wide massive binary system close enough to form a very close binary black hole system that is able to merge in the age of universe time due to gravitational wave emission. However, more and more recent study challenges this formation channel with common envelope, and it looks like so-called rapid population synthesis code could significantly overestimate number of common envelope events. And this is for two reasons. First is that a mass transfer in such a massive star binaries could be much more stable than previously thought. And the second one is that even if we developed unstable mass transfer in the binary system, it is very hard to get the successful envelope ejection and avoid the stellar merger of in the system. And this is a plot from Gallegos Garcia 2021 that nicely visualize those findings. So here we have a grid of black hole star binaries with the mass ratio and separation of the system, and the final outcome of after the second mass transfer phase. On the left, we have results from rapid population synthesis code, and on the right, we have results from detailed stellar evolutionary codes such as MESA. And as you can see, here in the rapid population synthesis code, there was this significant part of the parameter space which was believed to produce evolve later to binary black hole mergers that through the common envelope evolution. And this parameter space is no longer found in the, once revisiting the stability of mass transfer in the massive binary systems. So based on those similar findings, in particular based on Pawłowski et al. 2017, I created and implemented new criteria for mass transfer stability into the rapid population synthesis code. And this criteria no longer take into account only the donor type and the system mass ratio, but also consider the relation between the donor mass and the radius of the donor. And this criteria is in general much more restricted when it comes to the common envelope development. So as our basic formation scenario for binary black hole mergers used to be with the common envelope phase, we expected that such a restricted criteria for common envelope development would kill all the binary black hole mergers in our simulations. However, instead, we got a new formation path for binary black hole mergers with two stable mass transfer phases. So as you can see here, this system also goes through the stable mass transfer phase during the first system Roche Lobe Overflow. However, in contrast to this common envelope channel, the initial separation of the system is a bit closer, and therefore we expect that the mass transfer during this phase is rather conservative. So we can end up with a significantly reversed mass ratio of the system after the first mass transfer phase. And such a system with unequal mass components was expected to go through the common envelope phase and end up as a stellar merger after this common envelope phase within our previous criteria. However, once implementing the new criteria for the mass transfer stability, such a system goes through the stable mass transfer phase instead, and is able to shrink the orbit enough to merge, to form binary black hole merger that merges in the Hubble time. The important thing in this formation channel is that after this first mass transfer phase, there is a mass ratio reversal, and therefore system is in quite wide orbital, with quite wide orbital separation, and therefore, in order to tie the system enough during the second Roche Lobe Overflow, we need to have very unequal mass ratio at the onset of the second Roche Lobe Overflow. And that comes from the fact that once following evolution of the orbital separation as the response for the mass transfer, we are able to shrink the orbit only once the donor is more massive than the accretor. At least this is the result for the conservative mass transfer, when both mass and the angular momentum is conserved in the system. The situation is a bit more complicated when we have a highly non-conservative mass transfer, like, for example, here during the second Roche Lobe Overflow, we expect that mass transfer on the black hole is highly non-conservative, so also a lot of angular momentum could be lost from the system. So the final outcome actually depends also strongly on this assumption on the angular momentum lost with the matter. So this requirement of having highly unequal mass system at the onset of the second Roche Lobe Overflow in the stable mass transfer channel results in characteristic parameter space for the binary black hole progenitors. So here we have black hole star systems in our simulations at the moment of the first black hole formation. And as you can see, with the black dots, I mark the systems that later evolves into binary black hole progenitors, either via this stable mass transfer evolution or the common envelope subchannels. So as you can see, in case of the stable mass transfer channel, we need to have a very highly unequal system, and it tends to favor rather separations of around 100 days. While when it comes to the common envelope channel, it is important to have much wider separation at the onset of the second Roche Lobe Overflow in order to enter the common envelope once the donor has already well-developed convective envelope.
Excuse me, what's the color code?
The color, it's some sort of density plot. So yeah, the red color stands for when there is the dense grid of black hole star systems. Because in general, this is a a grid of black hole star systems that form in our simulations, in the rapid population synthesis code simulations. And these are black hole star systems in terms of their mass ratio and the orbital separation at the moment of the first black hole formation. So yeah, so this is some sort of density plot. So when it is, the color is not that good on this presentation, but the red colors are some density plots, like the dense regions where we expect to have a lot of black hole star systems. So already first Roche Lobe Overflow actually determines how this parameter space looks like and what kind of systems could be later favored. And that also impacts the final distribution. I don't know if that was clear.
Sorry, what's the difference between the black and the color shading? So the black points are the progenitors and the rest?
Yeah, so black points are black hole star systems that later, after the second Roche Lobe Overflow, evolves into binary black hole mergers via stable mass transfer channel or common envelope channel.
Red box.
Here?
The red box.
The red box. Yeah, so this is the result for low angular momentum loss during the second Roche Lobe Overflow that corresponds to the specific angular momentum of the accretor. Because this angular momentum, the assumption of the angular momentum loss during this second highly non-conservative mass transfer also impacts a lot which black hole star binaries later evolve into binary black hole mergers. So as you can see, these are very characteristic black hole star systems that later evolves into binary black hole mergers. And that actually impacts of course, the final parameters of the formed population of binary black hole mergers. And for our default model in the stable mass transfer channel, we expect that this formation scenario would favor formation of unequal mass binary black hole mergers with the typical mass ratio somewhere between 0.4 and 0.6. While this common envelope scenario tends to form rather equal mass binary black hole mergers. However, these are the results on this upper panel, and this green line stands for the our classic stable mass transfer formation scenario for binary black hole mergers. However, those results are, as I mentioned, highly sensitive to what we assume for the angular momentum loss for the system. And when we allow for much more significant angular momentum loss, so for example, when we assume that the matter lost from the system is lost with the specific angular momentum of the outer Lagrangian point, the mass ratio distribution is actually dominated by equal mass component binary black hole mergers. Also, other parameters, like, for example, the assumption on highly uncertain natal tips of the black holes could impact the distribution of mass ratio of those binary black hole mergers. So, to sum up, if future detections future gravitational wave detections would consist of a significant fraction of binary black hole mergers with their typical mass ratio something between 0.4 and 0.6. That could be consistent with our stable mass transfer formation scenario with low angular momentum loss from the system. So this is how the future gravitational wave detections could tell us something about the binary physics and could help us constrain, for example, angular momentum loss from the system during highly non-conservative mass transfer phase. And right now, the mass ratio distribution that is derived by LIGO-Virgo-Kagra is highly uncertain because also the derived individual masses of the systems are subject of the large bars, error bars. So actually, the result also depends a lot on what you assume on the prior distribution of in the Bayesian interference. So yeah, it's hard to say what is actual distribution of the mass ratio of the current gravitational wave sources. However, recently there was this paper, Rinaldi et al. 2023. And they did some sort of alternative analysis of the LIGO-Virgo sources and applying some different tools in order to do the data analysis. And they derived this sort of distribution for the mass ratio, which is highly consistent with what we get in our default model for stable mass transfer channel. So as the stable mass transfer channel and common envelope evolution seem to be much different when it comes to their efficiency in tightening the orbital separation during the mass transfer phase. They also result in some different distribution of so-called time delays. Time delay is the time between the binary black hole system formation to its eventual merger due to gravitational wave emission. So yeah, stable mass transfer channel in general results in longer time delays because it's less efficient in tightening the orbital separation with the exception of the highly unequal mass systems. So in fact, the stable mass transfer formation scenario, it could produce a lot of equal mass systems. However, their time delays is much longer than the current age of the universe. So they are not able to merge in the Hubble time due to the gravitational wave emission. While this standard common envelope prescription usually results in shorter time delays and also much more various distribution of the mass ratio. And that, on the other hand, this characteristic time delay distribution may affect the evolution of the merger rates as a function of redshift. So here we have, with the green line, we have evolution of merger rates of binary black hole systems that were formed through the common envelope evolution. And with the red curve, we have systems that form binary black hole mergers with this stable mass transfer formation scenario. And as you can see, there is this characteristic peak around redshift 2, which corresponds to the peak in the star formation rate in the universe. And once the time delays are longer for the stable mass transfer channel, this peak is shifted a bit towards the lower redshift values. And so actually by measuring the slope, which may soon be possible with the future gravitational wave sources, we would be also able to say something about the distribution of the time delays and therefore put some constraint on the efficiency of tidaling the orbital separation and maybe even distinguish between different formation scenarios. So yeah, at the end, I would like to tell a few words about the black hole spins. So the current gravitational wave sources are consistent with black hole population dominated by low but non-zero black hole spins. So there is a peak at around 0.2 and the long tail extending to the higher black hole spin values. So such a distribution dominated by low black hole spins, low natal black hole spins, would point toward efficient angular momentum transport in the massive stars, because we need to have some sort of efficient mechanism that would transport the angular momentum from the rapidly rotating core to the outer layers of the stars that could be later, for example, removed due to the binary interactions. However, in order to fully reconstruct the observed distribution of black hole spins, so also reconstruct this tail for the high black hole spins, we need to have some other mechanism that would allow for spinning, like get the higher spin of one of the black holes. And there is this theoretically predicted mechanism in the close binaries of black hole and stripped helium core, and with the separations of only around 1 day, that is expected to, in such a system, it is expected that the black hole may tidally spin up its helium core companion, and therefore this helium core may spin up and end evolution as a highly spinning black hole. So once applying those two assumptions, so the efficient angular momentum in the massive stars combined with the possibility of those tidal spin up of the helium cores in the very close black hole helium core binaries, we are able to quite well reconstruct the observed spin distribution of binary black hole mergers. Okay, so here is the summary. So right now we have around 90 binary black hole detections together with some estimates for their masses and their spins. However, the origin of those binary black hole mergers is still unknown, and due to the high degeneracy in the modeling and a lot of uncertainties in the modeling for different formation channels, it's hard to constrain contribution of the different formation channels. Isolated binary evolution channel with and without common envelope phase is doing quite well with reconstructing so far observed parameters of binary black hole mergers, such as the distribution of the masses, spins, also some more exotic events with unequal mass ratios or higher spins. And there is this relatively new formation channel, the formation with stable mass transfer via stable mass transfer channel, which is not yet well studied, and however it may also be a promising formation channel that could contribute to the current population of the gravitational wave sources. Yeah, and in the end, this is the result from the paper that hopefully will be submitted soon. So once we would be sure that there is significant fraction of binary black hole mergers with a characteristic mass ratio somewhere between 0.4 and 0.6, that could indicate contribution of the stable mass transfer formation channel. And that would be also consistent with our formation scenario with mass ratio reversal during the first Roche Lobe Overflow in the system and low angular momentum loss during the second highly non-conservative mass transfer phase. Thank you, and I'll be happy to answer the questions.
A question? Okay, I have the question. So in the case of the second stable mass transfer, we expect that accretion disk will be formed around the black hole, and the system will be X-ray bright, and we see the jet ejection and stuff like that. Yes.
Yes.
And we expect some growing of the mass of the black hole, and what it will be this gain?
Growing, yeah. Okay, yeah. I guess what is currently understood that the mass accretion is in this kind of system is not very efficient. So even if the system, the system, such a black hole during this kind of stable mass transfer phase would not accrete more than, I don't know, 10% of its mass, and most of the system would be actually lost from the system. And so that would not significantly affect the final distribution of the binary black hole mergers.
Okay. More question? Okay, Wodek.
Still a related one. Is there a way to distinguish a merger that occurs in vacuum from one that occurs inside the common envelope?
Sorry, can you repeat the question?
Right. So the merger, when it occurs, is it clear that the two black holes are in vacuum and not inside?
Some environment. Yeah, I mean, it's not that clear, and actually those mergers that origin from AGN disks are could be somehow followed by some electromagnetic counterpart, as they are in the presence of some environment. So they are some studies that, for example, search for some coincidence between when we detect binary black hole merger, and if at the similar time you can find some sort of the signal in electromagnetic waves that could be somehow related to that binary black hole mergers. But so far, I think there was only one case like this, and it was not very convincing, like it could be just a random thing. But yeah, people do consider this kind of scenario, and that would for sure help us to distinguish the formation scenario, because if we really be sure that the binary black hole merger was somehow
Okay. So is there any spin dependence of the different formation channels? Dependence on the chi?
It's quite hard to say, because it's also quite model dependent, but in general, you would expect that isolated binary evolution tends to produce a distribution dominated by low effective spins, while for example, dynamical formation scenario they could once they could produce higher spins, because some of the events could be like the second generation merger, and the product of the former binary black hole merger is expected to have high spin. So this is the one thing, and the other thing is that the orientation of the spins is expected to be rather randomized. So there could be like for this kind of dynamical origin binary black hole mergers, you would expect to have also a high contribution of negative effective spins that due to this high misalignment, while isolated binary evolution is expected to result in rather aligned spins in the binary black hole mergers. However, that is also like still not well constrained. But this is the general what people think.
Radek?
So you talked about rapid population synthesis code. How it differs from just population synthesis code, and I understand it probably faster, but does it have any additional simplifications, assumptions?
No, I mean it's the same. It's just a popular name right now for the rapid population. You just try to distinguish it somehow, and maybe also put some value on why actually people use those codes, because they are rapid and they are able to evolve a large population of binary systems, while those detailed scalar evolutionary codes consume much more time. But yeah, it's just it's just the population synthesis codes.
Okay, we have the question from Łukasz.
Okay, hello. Very nice talk, Ola. Thank you very much. I'm intrigued by the plot you showed at slide number 6, which showed the double peak distribution of binary black hole merger masses. So I looked up the paper, and it's 2021, and it's based on, it's not the full sample of events yet. It's like half of it, right? So the question is whether it has changed much when new cases were added from newer runs, and how does it look?
I think this is already the third run. I don't remember how many of them are included, but I think this distribution did not change much between the second catalog and this third catalog, and I think it wouldn't be affected once adding maybe it was after the O3A, and there are also some other detections from the O3B. I don't think that it would actually change much. The point is that it strongly depends on what you, for example, assume on the prior for the population. So sometimes you may also get some different shape, but it's not like the case of number of detections, but rather what kind of prior assumptions you choose for.
But then this secondary peak, is it kind of strong, significantly strong, or it's very dependent on the assumptions?
Yeah, I think it is quite strong, but I still wouldn't fully rely that. I mean, that is 100% some astrophysical origin. But yeah, I think that those two features are quite strong, and they were also reported already in the previous catalog. So I think, they could mean something, but it's not still 100%. I hope that the future detections would help us to constrain whether they are really there or not.
Okay, thank you.
Okay, thank you. Okay, we have the one question more. You ask for the units on the axis.
Okay, so what are the units here on this axis? So this is some sort of derived merger rate in terms of per gigaparsec cubed per year per the mass bin. So it tells you something about what is the derived merger rate once getting rid of the selection biases per some unit of mass. And it is expressed in the similar unit as, for example, star formation rate. So yeah, it's per gigaparsec cubed per year.
Okay, so I don't see more question. Let's thank our speaker again. Thank you very